All right, so I unfortunately realized that our PowerPoint notes, the fill-in notes, did not really address the first or second law of thermodynamics explicitly or directly. So I want to go over them with you guys real quick and just see how everything ties in with heat and entropy and where we see these in the laws. So the first law of thermodynamics says that energy, which we've been seeing as heat in this whole unit, is neither created nor destroyed, but is transferred from one form to another, right? And so the most common place we see that is calorimetry problems, right? These are those ones where we have the heat of a metal, some hot metal, that's what M stands for, placed in a calorimeter filled with water, right? And we try to solve for something typically like the specific heat capacity of the metal, right? So we've done these problems before, and that's a perfect example of the first law of thermodynamics, because heat equals one heat from the metal, the hot heat from the metal equals the heat that the water is absorbing, right? The metal is releasing heat, that's why it's negative, and the water is absorbing it, right? But they equal each other. It's not getting destroyed, it's not going away, it's not getting larger, it's not like we have a 2 here or anything like that, or a half here. It's Q equals Q. It's just one's negative because one's releasing it and one's absorbing it, right? So that's why we get this whole thing here. So we've been seeing the first law of thermodynamics in action just by looking at these problems. And we know that the heat, which is the letter Q, has units joules. Sometimes you see kilojoules, but the base unit is joules. Right, so that's the first law of thermodynamics. Again, heat's not being created or destroyed. It's just being transferred from one form to another. The magnitude of these are the exact same. The number is the same. It's just one's negative because it's exothermic, it's releasing it, and one's positive because it's endothermic, it's absorbing it. So the second law of thermodynamics is all about entropy and disorder. So the second law says the total entropy of an isolated system can never go down over time. It can never go down over time. So that just means the measurement of disorder and randomness of any isolated system can only ever be increasing or stay constant, right? If it stays constant, it technically has to be reversible. It has to be able to go backwards, but it can never go down. It can never get more orderly, right? So if you see a pile of bricks on the ground, it's never gonna suddenly become more orderly and build itself into a brick wall, right? A brick wall is way more orderly than a pile of bricks. So if you see a pile of bricks on the ground, it's only ever gonna get more disordered, or it's gonna just stay constant. If you go up to the bricks and try to cement them and build a brick wall yourself, it's not an isolated system anymore because you're interfering with it, right? Kind of like an ice cube. If I have an ice cube hanging out at room temperature out here in the open, it's only ever gonna at least stay an ice cube, or it's gonna possibly melt, right? If I want it to get any colder by putting it in some ultra freezer and getting it even colder than it is, I have to pump in extra energy into the system via electricity. It's not an isolated system in that case, right? So entropy, the disorder, the randomness of a system can only ever increase, or it can stay the same for an isolated system, right? If it gets more orderly, then it's an open system, right? If I go up to that pile of bricks and get some cement and build a brick wall, it's an open system. I'm interfering with it. If I want the water to get colder and not, evaporate or not stay as a puddle of liquid water, if I want it to freeze into ice, I have to put it in the freezer. That's an open system because I'm adding in extra heat to the system via electricity, right? That's not isolated, that's open. So the units of entropy are joules per Kelvin, right? Just keep that in mind, joules per Kelvin are the units. And the important thing about the second law of thermodynamics is it really proves why heat always goes from hot to cold. Now we know this intuitively. We know that heat travels from hot objects to cold objects. There's really no such thing as coldness. It's just a lack of heat, right? But the second law really explains why. So it explains why heat goes from hot to cold objects, kind of like what we saw up here with the calorimetry problem. The metal was hotter, the water's cooler, so the metal was releasing the heat. The metal was negative. So let's take a closer look into this, because we know that heat goes from hotter objects to cooler objects. The C is cool, the H is hot, right? So this is going to be negative, it's releasing it, and this is positive, it's absorbing it. But let's see why. All right, so taking a look up here, entropy, which is delta S, is really heat per temperature, because the units are joules per Kelvin, right? Joules per Kelvin. So joules per Kelvin are the units, which is heat per temperature, right? So if I think of some sort of isolated or some sort of system of two objects, one's hot, one's cold, and I try to get the total entropy of both of them, this is the entropy of the cold object, this is the entropy of the hot object, right? Let me just substitute into these values the equation I have here for entropy, Q over T. Right, so this is what I get. So I have the heat of the cold object over the temperature of the cold object, the heat of the hot object over the temperature of the hot object. And I'm putting this negative here because we know hot objects release the heat, they're exothermic, the cold objects are going to absorb that heat. But we're going to prove why, right? I know I'm just putting this here right now just because of our experience in everyday life, but we're going to show why this has to be here at the end of all this. Right, so if we recall the first law of thermodynamics, the first law says heat can never be created or destroyed, it just transfers from one form to another. So QH, the heat from the hot object and the heat from the cold object, they're really the same. So I don't need this C and I don't need this H, I can just call them both Q, right? They're both the same, so I'm just gonna call them both Q. So this is what I get down here. Ignore that, that shouldn't have been there. So we have Q over the cold temperature minus Q over the hot temperature. They're both Q because it's the same energy, the first law of thermodynamics, right? Heat can't be created or destroyed, just transferred from one form to another. And we know that a temperature that's for a hotter object is going to be a higher temperature than a temperature for a cold object. It's the same Q, right? It's the same heat up here, the same numerator, the same Q. But this temperature is going to be a small number, this temperature is going to be a big number. So since this is going to be a bigger denominator because it's a hotter temperature, this overall fraction here should be smaller than this fraction, right? So let's just plug in some random values. Let's just say, for the sake of this discussion, the heat going between both of them is 50,000 joules, 50 kilojoules. The cold temperature is something small, like 5 degrees Celsius. The hot temperature is something large, like 90 degrees Celsius. Let's just say that's what's happening. So let's plug in our values, right? So it's getting everything down here together. So again, the heat's the same between both of them. It's 50 kilojoules, because of the first law of thermodynamics. But the cold temperature is this small 5 degrees Celsius. The hot temperature is this larger 90 degrees Celsius. Now, just to kind of get things in the correct units for joules per Kelvin, right, because it's joules per Kelvin for entropy, I'm just going to go ahead and convert the Celsius to Kelvin by adding 273 to both of them, and I'll just turn this into 50,000 because it's 50 kilojoules. So let's just go ahead and show that real quick. Ignore that mistake there. Sorry about that. Scribble. So 50,000 joules over 278 Kelvin minus 50,000 joules over 363 Kelvin. So we can tell this is going to be a bigger number than this, because it's the same numerator. It's 50,000 on the top, 50,000 on the top. It's the same numerator, but this is a smaller denominator. This is a bigger denominator, right? Even looking at this here, of the 5, you can tell this is going to be 10. This is going to be something less than 10, right? Same thing here. So let's see what we get. I get 179.9 joules per Kelvin minus 137.7 joules per Kelvin. So the overall change in entropy here is positive 42.1 joules per Kelvin. It's positive. So the second law of thermodynamics said that the entropy can only increase, it can't go down. It can stay the same, but it cannot go down. If the entropy is going to go down, which it can't, this is a law, it can't go down, then it has to be negative. So if entropy is going down, if it's decreasing, then it's negative. So I can't have a negative answer here, right? Luckily, I got a positive answer. I have positive 42.1 joules per Kelvin, and this can only happen if the entropy or the heat from the hotter object is negative. So I know we said before I put a negative here because of experience in everyday life. We know hot objects release heat. We know cold objects absorb heat. But the reason why it goes from hot to cold, the reason why heat flow goes from a hot object to a cold object is because I need the overall entropy to be positive, or at least stay the same. So this can be positive, or this could have been 0. It could have been 0, that's fine too, but it can't be anything negative, right? Because if I did the opposite, for example, if I made this negative, if I made the cold negative and the hot positive, if I put this a plus sign here and a negative sign here, then I would have gotten negative 42.1, which would go against the second law of thermodynamics. right? So in order to make sure that this is not negative, but it's positive, to have entropy increase for an isolated system, I need the heat to be negative for a hot object. The hot object has to release the heat. It has to be exothermic. All right, so we're never gonna have to use these equations for like the test or anything. You're not gonna ever have to plug in values for this stuff. Don't worry about that. I just want to show you guys this thought experiment just to kind of explain why the second law of thermodynamics effectively proves that heat goes from a hot object to a cold object. We know this in our everyday life, but the second law basically explains why, and it has to do with entropy, right? The measurement of disorder and randomness in a system cannot go down. It can only increase or stay the same. And then of course we use the first law on this as well, because the heat's never created or destroyed, it just stays the same. That's why earlier we just made these both Q, and it was the same 50,000 joules. But anyways, that's the last notes for the unit.